Hello everyone. In the beginning of today's class, let us see new announcements. Okay, the first new announcement is May 11th, 2022 class videos uploaded. Okay, hello everyone. I have uploaded the class videos on May 11th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the next new announcement is the slides of Chapter 3 has been updated, version 2022-0513. Hello everyone, I have uploaded the latest version of the slides of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, slides. Chapter 3 slides 2022-0513.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of Chapter 3 has been updated, version 2022-0513. Hello everyone, I have uploaded the latest version of the handout of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, handouts, Chapter 3, handout 2022-0513.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. Okay, in the last class, we have taught to Chapter 3 slides, page 194, 24 bits per second per hertz. Then we go to figure 3.10. Okay. So please open the slides of Chapter 3. Okay, and please turn to page 194. Okay. Okay, we are talking about the outage capacity. For example, at rho being equal to 10 dB, Cout1 is approximately 24 bits per second per hertz. Okay, let us go to figure 3.10. Okay, we can see that when rho, that is SNR, is equal to 10 dB, this line, okay, and N is equal to 10, okay, we can see that the channel capacity is approximately 24 bits per second per hertz. Okay, and Cout10 is approximately 26 bits per second per hertz when N is equal to 10. Okay, let us go to figure 3.11. Okay, when SNR is equal to 10 dB and N is equal to 10, okay, the channel capacity is approximately 26 bits per second per hertz. Okay, by comparison, the ergodic capacity for the same number of antennas is approximately 28 bits per second per hertz. Okay, let us go to figure 3.8. Okay, when SNR is equal to 10 dB, okay, this line, and N is equal to 10, okay, we can see that the channel capacity is approximately 28 bits per second per hertz. Okay, the outage capacity results in these figures were obtained using computer simulations. In the case of SIMO and MISO systems, relatively simple closed-form solutions exist for the outage capacity that can be used in place of Monte Carlo computer simulations to make performance predictions. Okay, what is the Monte Carlo computer simulations? Let us go to handout. Okay. Okay, so page 195, problem 1. What are Monte Carlo computer simulations? Solution: Monte Carlo methods or Monte Carlo experiments are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. Okay, let us go back to the slides. Okay, next page. In the following, we derive an expression for the outage capacity of a SIMO system. It is straightforward to extend this result. Okay, that is, it is easy to extend this result. That is the outage capacity of a SIMO system to a MISO system, which is left to you as a problem at the end of the chapter. We begin the derivation by recalling from equation 3.43. Okay, let us go to equation 3.43. Okay, this is SIMO capacity. C SIMO CSIR, that is, only the receiver know the channel state information, is equal to log 2 of 1 plus rho times the square of the Frobenius norm of H, where H is the channel matrix. Okay, that the instantaneous capacity for a SIMO channel is C is equal to log 2 of 1 plus rho times the square of the Frobenius norm of H. Okay, therefore, using the definition of the outage capacity, it follows that the probability of log 2 of 1 plus rho times the square of the Frobenius norm of H is smaller than or equal to C out Q, okay, which is equal to Q, which implies that the probability of the square of the Frobenius norm of H is smaller than or equal to 2 to the power of C out Q minus 1 over rho, which is equal to Q. If we assume that H is equal to HW, then the square of the Frobenius norm of H is equal to summation I is equal to 1 to NR. The real part, the square of the real part of HW of I plus the square of the imaginary part of HW of I. Okay, it is equation 3.55. Okay, how do we derive this equation? Please see the handout. Okay, page 198. Problem 1. Derive equation 3.55. Solution. By the assumption that H is equal to HW and the definition of the Frobenius known, we know that the square of the Frobenius known of H is equal to the square of the Frobenius known of HW, okay, which is equal to summation I is equal to 1 to NR, okay, summation J is equal to 1 to NT, square of the absolute value of HW of IJ. Okay, where NR is the number of receive antennas and NT is the number of transmit antennas, HW of IJ is the IJ's entry of the channel matrix HW. Now, because we consider a simul system, NT is equal to 1. Then HW becomes an NR by 1 vector. Let HW of I denote the ith element of HW. Then the square of the Frobenius known of HW is equal to summation I is equal to 1 to NR, the square of the absolute value of HW of I, and it is equal to summation I is equal to 1 to NR, the square of the real part of HW of I plus the square of the imaginary part of HW of I. Okay, so this completes the derivation of equation 3.55. Okay, let us go back to the slides. By definition, the real part of HW of I and the imaginary part of HW of I are normal distributed random variables with zero mean and variance 1 second. Okay, in general, the sum of the square of n zero mean Gaussian random variables, each with variance sigma square, has a gamma distribution with the following probability density function. F capital X of small x is equal to 1 over 2 times sigma square to the power of n times gamma of n over 2. Okay, what is gamma of n over 2? Now let us see the handout. Okay, page 199. Problem 1. What is gamma of n over 2? Solution. Please see figure 5. Okay, figure 5 is the gamma function along part of the real axis. Okay, so this is the gamma function. Okay, like this. Okay, let us go back to the first time of figure 5. Okay, here. In mathematics, the gamma function represented by gamma, the capital letter gamma from the Greek alphabet, is one commonly used extension of the factorial function to complex numbers. The gamma function is defined for all complex numbers except the non-positive integers. for any positive integer n, gamma of n is equal to n minus 1 factorial. Derived by Daniel Bernoulli for complex numbers with a positive real part, the gamma function is defined via a convergent improper integral. Okay, gamma of z is equal to the integration from 0 to infinity, and x to the power of z minus 1 times exponential minus x dx, where the real part of z is greater than 0. Okay, let us go back to the slides. And then times x to the power of n over 2 minus 1 times exponential minus x over 2 sigma squared. Okay, denoting the square of the Frobenius norm of h by x, it follows from equation 3.54 that, okay, let us see equation 3.54. Okay, in equation 3.54, the probability of the square of the Frobenius norm of h is smaller than or equal to 2 to the power of C out q minus 1 over rho, which is equal to q. Okay. So let us compare equation 3.56 and the previous equation 3.55. Okay, the sum of the square of n0 mean Gaussian random variables, each with variance sigma square. Now in equation 3.55, okay, they are nr times 2. Okay, the sum of the square of 2nr 0 mean Gaussian random variables, each with variance sigma square is equal to 1 second. Okay, so now n is equal to 2nr and sigma square is equal to 1 second. Okay, so equation 3.56, okay, we can see that, okay, q is equal to the integration from 0 to 2 to the power of C out q minus 1 over rho f of the square of the Frobenius norm of h of x dx. Okay, and the PDF becomes, okay, 1 over 2 sigma square. Okay, and sigma square is equal to 1 second. So 2 sigma square is equal to 1. And 1 to the power of n, where n is 2nr, is also equal to 1. And the gamma of n over 2 becomes gamma of nr. Okay, so here is a constant 1 over gamma of nr here. Okay, and the integration from 0 to 2 to the power of C out q minus 1 over rho, okay, it is the same as the last equation. Okay, and xn over 2, now n is equal to 2nr. So this term becomes x to the power of nr minus 1. Okay, so here is the term x to the power of nr minus 1. And exponential minus x over 2 sigma square. And now sigma square is equal to 1 second. So this term becomes exponential minus x. Okay, so here exponential minus x dx. Okay, where the integral expression on the right side of the equation is recognized as being the incomplete gamma function. In general, the incomplete gamma function is denoted by p of xa and is defined as p of xa is defined as 1 over gamma of a times the integration from 0 to x t to the power of a minus 1 times exponential minus t dt. Okay, thus we can express equation 3.57 as, okay, let us go to equation 3.57. Okay, is this equation. Okay, then compare this equation, equation 3.57 and equation 3.58. We can find a is equal to nr and x is equal to 2 to the power of c out q minus 1 over rho, and a is equal to nr again. Okay, so we know that equation 3.57 is p of xa, where x is equal to this term and a is equal to nr. Okay, so q is equal to p of 2 to the power of c out q minus 1 over rho nr. It follows from this equation that we can express the Q% outage capacity for a 1 by nr SIMO system in the following compact form. C out Q is equal to natural log 1 plus rho times P inverse of QNR over natural log 2. Okay, where P inverse of YA denotes the inverse incomplete gamma function, which is defined such that P inverse of P of XA A is equal to X. Okay, how to derive equation 3.60? Let us see the handout. Okay, page 202, problem 1, derive equation 3.60. Solution from equation 3.59, we know that Q is equal to P of 2 to the power of C out Q minus 1 over rho nr. Okay, now that P inverse of YA denotes the inverse incomplete gamma function, which is defined such that P inverse of P of XAA is equal to X. Then, okay, we know that this term is X and NR is equal to A. Okay, so X, that is 2 to the power of C out Q minus 1 over rho is equal to P inverse of P of XA, and P of XA is equal to Q. So it is equal to P inverse of QA, okay, where A is NR. Okay, so this term is equal to P inverse of QNR. And multiply both sides of this equation by rho, it implies that 2 to the power of C out Q minus 1 is equal to rho times P inverse of QNR. And it implies that 2 to the power of C out Q is equal to 1 plus rho times P inverse of QNR. Okay, taking log 2 on both sides of this equation, it implies that C out Q is equal to log 2 of 1 plus rho times P inverse of QNR. Okay, and okay, it is 25 minutes. Let us take a break.